In this lesson, we'll go over the force on a current in a magnetic field. So, in a previous lesson, we learned that if an electric charge is moving through a magnetic field, that electric charge will experience some force. The same thing will happen if there's a current passing through a wire, because all a current really is a bunch of electric charges moving in a straight line. We'll start with a little bit of just a fact here to write down and memorize. I think I should read it first. Magnetic force can only act on moving charge, but that's exactly what a current carrying wire is. Magnetic force can only act on moving charges, but that's exactly what a current carrying wire is. In order to develop an equation for this type of force in this circumstance, we can actually start with the equation for the magnetic force, the one that we saw for a current carrying wire. And that is FB equals QV B sine theta. So as a reminder, FB is the magnetic force, Q is the amount of charge it's acting on, V is the velocity of that charge, B is the magnetic field strength, and theta is the angle between B and V. We're going to substitute two equations that we saw in a previous chapter, the chapter about current. I'll write it off to the side in case you want it. It's the fact that, we're going to do something else. We're going to multiply top and bottom by t. So we're going to go like this. We're going to multiply this by t over t. T over t is equal to 1. So I'm not changing the equation at all. I'm just multiplying the right-hand side by t over t. I'm multiplying the right-hand side by 1. We'll take one of these t's and pair it up with the velocity, take the other t and pair it up with the charge. And something kind of cool is going to happen here. So we'll have q over t. So I took the bottom t and put it under q. And then v will make it vt. The rest remains as is. FB equals Q over T times VT times B sine theta. We're not going to want to cancel out those T's because we just put them in there for a reason. By pairing them up with these, we'll find that they actually mean something. So this is the equation I was going to write off to the side. It's from our last chapter. Q over T, charge per time, is the exact definition of what current is. That's the equation that we wrote down in lesson 6.1, I believe. So the amount of current is charge over time. So this is really just current. It's the current passing through the wire. Velocity times time, we could find that by going like this. Velocity is distance over time. So really, velocity times time is the distance traveled by the charges. In the context of a wire, though, that's going to be the length. So velocity times time is the length or distance traveled by the charges in the electric wire. And magically, we've developed a new equation. So the magnetic force acting on a wire, a current carrying wire, is equal to the current in that wire times the length of that wire times the magnetic field strength passing through that wire times the angle between, sine of the angle between B and L. Well, I guess, yeah, that's interesting. It's the angle between B and L, or the angle between B and I, because I and L are going to point in the same direction. It's just a wire. So you can label those if you wish. That's current. The other two I think I might leave just because I'll label them. Current represented in amps. This is length in, what am I underlining it for? Meters. B is the mag field, measured in Teslas. And theta, I'll just say angle between I and B. Of course, FB is magnetic force. Why not? Let's just label it. In newtons. I'm going to discuss a little bit of the direction of this. Yeah, there's actually a great image right here. So the right-hand rule still applies here, and it actually applies in the same way. I don't see why they felt the need to do another image here, but I think it's worth talking about. So just like before, the magnetic field could be represented by the fingers of your right hand. The force could be represented by the palm of your hand, and I represents the current. The interesting thing about current in physics is that although the electrons are the things that are moving, we treat current as a motion of positive charges. So this is the motion of, quote, positive charges, even though it's more like the absence of electrons. I should discuss that later. That sounds like a cool idea. Anyway, so yeah, you point your thumb along the wire, the direction of the current. We can see I as an arrow there. You point your fingers along the magnetic field, and as we can see in this picture, that means the force is going out of the palm that way. Let's see an example of this problem. We're going to look at a loudspeaker. This is how speakers work. So speakers have a magnet on them, and the magnet causes force to be pressed on the speaker cone. I need to check how much time I'm on here. Okay. Here we go. So I'll probably have to show you an image. I'll read it while I show you the image. Where's my next one? There we go. So this is the image of a loudspeaker. It says, the voice coil of a speaker has a diameter of 0.025 meters, contains 55 turns of wire, and is placed in a 0.10 Tesla magnetic field. The current in the coil is 2.0 amps. Calculate the force acting on the coil and the cone. Write it down, please. The voice coil of a speaker has a diameter of 0.025 meters, contains 55 turns of wire, and is placed in a 0.10 Tesla magnetic field. The voice coil of a speaker has a diameter of 0.025 meters, contains 55 turns of wire, and is placed in a 0.10 Tesla magnetic field. calculate the force acting on the coil / cone if the current is 2.0 amps. Calculate the force acting on the coil in the cone if the current is 2.0 amps. Okay, maybe back to the picture here. So there's going to be no force acting on the cone itself, actually, because there's no current passing through there. The only force will be acting on the coil. In reality, it's acting on the charges in the coil. So we have this magnet here. It's a very strangely shaped magnet. We have a north in the center and a south on the outside. And because of that, the way it's shaped, like in this circular shape, the force is always going to press outwards. So placing your fingers across, like you'd have to place your fingers into the page. I don't know how to show it on my screen here. But it would be, yeah, the force is always pressing out. On this wire it's pressing out, on this wire it's pressing out. So like you send charges through here and it causes this to oscillate back and forward, creating some sound. It shakes all the air and creates some sound. Calculation is quite simple, actually. I'm going to complete the calculation on the left, but I'll start it on the right-hand side. Feel free to, let's give it a quick draw. Really tough to draw that picture that we had there. Maybe you can do better than I. So there's like a south pole in the middle. Ooh, I'm already doing horrible. North pole on the outside. And we've got our coil. And the coil includes the only twist in the problem. Okay. So they gave us a diameter of, what was our diameter? 0.025. But we don't care about the diameter. We want the length of this wire. It's coiled and coiled and coiled and coiled. We want to know how long would this wire be if I stretched it out and got the full length of it. So really it's kind of a trick question here. They want you to use the circumference. I guess I can do the whole calculation here. Circumference times 55. So the circumference is the total length around. It's around this. And then there's 55 of those. So we want to know how many total turns. So there's 55 total turns. How much length is each turn? And to figure that out, we can use our diameter. Where's this coming from? Pi diameter? Well, circumference is equal to pi times the diameter. That's just a fact of math. In math, they might say that circumference is equal to 2 pi r as well. Same equation, just written in a different way. So pi times the diameter will be the length of one coil. They say there's 55 turns, so it goes around 55 times. This will get us the full length. So it's going to be pi times 0.025 times 55. I'm going to leave that there, and we're going to use that in our final calculation. Ultimately, we want to calculate the force acting on the coil. And so that is our new equation here. I'll start up top here. FB equals ILB sine theta. I believe the rest of it was given. So I represents current. Let's see if we can find current in here. There's diameter, turns. Tesla's is our magnetic field. There it is. 2.0 is our current. The length is found with this equation over here. So length is pi times 0.025 times 55. That'll be the length of the whole wire coiled up in there. B is magnetic field. I can see it right here, our capital T for Tesla, 0.10. And the angle is going to be 90. Why is the angle 90? Let's see if we can find that in the picture. You can kind of see it in the picture here. The current is going into the page, and the magnetic field is pointing like this. So there's a 90-degree angle between those. If I were to rotate this picture, like, let's see if I can go to my drawing or something. Very hard to visualize. So it's going into the page, and the magnetic field goes like that, so my fingers look like this. Really hard to see, but that's just the challenge of 3D physics. Usually, when in doubt, just go with 90 degrees. Usually the angle is just given in these problems, but if you're not sure, let's go with 90. 0.864 newtons. Make sure your calculator is in degrees. In fact, I did not make sure that my calculator was in degrees, so I'm going to double check. I'm pretty sure I was in radians. 2 times pi times 0.025 times 55 times 0.1 times sine of 90 should get 0.863. I rounded up to 0.864. The unit for all forces is newtons. Probably stop there, unless there's anything else to talk about with this image. I think it's a brilliant looking picture. If you're feeling clever, go ahead and draw that thing. That's a pretty cool looking picture. It'll help you visualize. Remember that a circle with an X represents an arrow pointing into the page, like a pen pointing into the page, and a circle with a dot represents an arrow coming out of the page. So there's an arrow pointing into my page, arrow pointing out of my page. It would be cool if we could do 3D drawings, but hey, we've just got paper here. Go ahead and post these solutions on Google Classroom. If you've got questions, let me know.